So as mentioned, I'm Alan Fryer. I'm with Ross. I work in the hyperconverged group, and I lead the NMOS and NDI activity group within AMWA. So I'm going to start off by answering the simple question of why are we doing this? Why do we want to add NMOS support to NDI? So NMOS has a mandate to provide a comprehensive control specification for IP media facilities, which it's not just a 2110 thing. So many people look at ISO 4 and ISO 5 as, this is how I discover and connect my 2110 devices, but it's got much broader possibilities than that. So we wanted to expand that, and recognizing that NDI really is growing into more of the broadcast space. It's had its sort of traditional roots in sort of pro AV and more simplified topologies, but now large broadcasters and medium-sized broadcasters are seeing the value of NDI. So it makes sense that we want to be able to integrate this into our control space under a unified control specification. So, about a year and a bit ago, we made a proposal into AMWA, and they have accepted an activity that we're working on that will become what's called BCP 00701 NMOS with NDI. So, what is that? So, BCP documents are best common practices. And these are documents that supplement the core IS or interface specification documents that sort of govern how NMOS works. So it's a way to create add-ons for specific applications. And some examples of this are, we have the BCP 006 series of documents that are adding codec extensions. So BCP 00601 is H.264. BCP 00602 is H.265. There are additions for JPEG access and so on. The 007 series are for transport extensions, and the first one is for NDI. And between the good work that's happened with the 006 group and the work that my team is doing on 007, we sort of laid down the foundations of how to create these frameworks that it makes it easy to add more. So we're doing NDI now, but in the future it will be easy that we've sort of knocked down a few of the roadblocks internally within the specifications to make it easy to add different types of transports for NMOS to make it that universal control plane for any type of media, be it on-prem, be it in cloud, anywhere. So BCP 00701 is specifically extends ISO 4 and ISO 5 for use with NDI. We do have a dependency actually to a revision that's required for ISO 5 that we discovered in the process of doing this. And that work is sort of pending into the AMWA, NMOS steering and architecture groups to make those extensions. Currently, ISO 5 has some limits that do not allow us to add the extensions into the transport and media types that we require. The schemas are just too restrictive. So there will be a revision that comes that will make it more universally possible to add these new transports. And so for the next activity that comes along for the next transport won't have any barricades, and they'll be able to just create a new BCP document. And for some reason, that picture was supposed to come up at the beginning of the slide. Okay, so what is NDI? So NDI is a complete streaming solution. So it consists of codecs, it consists of containers, transports, and control tools all bundled into one. So it's kind of a lot of things. Some of the advantage of it is that it's very easy to set up and manage. They have free tools. It's really had been designed to work on a single LAN segment. They've added some support for multi-segment bridging and so on, but it's really been focused at very simple networking. And typically for small number of devices, we'll say tens of devices, not hundreds and thousands of devices. However, a lot of broadcasters are finding value in using this still within their environment and perhaps bridging that into a 2110 environment where they will have their larger core enterprise routing but have these localized areas of NDI. So having this control plane makes a lot of sense. There are a couple of variants of NDI. There's what's called NDI high bandwidth, sometimes called full NDI or NDI a full bandwidth. NDI HB is a acronym that I'm starting to see used more often. So this is a very low latency. It uses a semi-proprietary codec. It's an MPEG-2 based codec that's called SpeedHQ. The audio is uncompressed. And that's the original form of NDI. And often when people say NDI, this is what they're referring to. In the last few years, new variants of NDI have been released called NDI-HX, or a high efficiency. And these utilize more standardized codecs, so H.264, H.265 codecs. And there are a couple of flavors of it that are optimized for different use cases. So HX2 is really for low bandwidth utilization. HX3 is more optimized for lower latency at the expense of higher bandwidth utilization. The original HX is actually a subset of HX2. So typically you'll see HX2 and HX3 are what are generally supported by devices. Okay, so let's talk about the activity of NDI and NMOS. So setting a couple of ground rules of what we set out to achieve and what we're deciding we're not going to achieve. So because NDI is a semi-opaque plug-and-play technology, it has an SDK, you give it very basic connection information, and it kind of figures it out. So our goal really was to provide a mechanism to provide discovery and connection capabilities within NMOS for NDI devices. Our goal was not to try and model everything that the NDI SDK and APIs are doing because they're not always readily apparent without a lot of digging and often are very device specific. So we decided that we're going to limit our scope to being able to discover devices and connect devices. And much like most NDI workflows are done today, NDI kind of handles the magic itself. So let's not try and, constrain it too much. We wrote this around the NMOS Advanced SDK version 5.5, which was the latest that was released at the time we started the activity. In review of the 5.6 and the 6.0 SDKs, we're not breaking anything. However, our mandate is still that 5.5 is what we sort of set our line as this is what we've tested and proven. The standard SDK, so this is the free SDK, is also supported. There are certain aspects that the free SDK does not support, and they're not mandatory. The BCP007 will work with devices that only implement the standard SDK as well. There will just be certain features that you can't utilize. And a really key goal that we had is that if you're implementing NMOS with your NDI devices, this should not preclude native NDI behavior. So if I've got an NDI device that's under NMOS control, I should still be able to go within the NDI ecosystem and make those discoveries, make those connections, and I don't break it. So that was really, really important. So we made some definitions within the specification. So we came up with the term native NDI device, sender, receiver, stream, and those refer to the terminology that exists in the NDI realm, in the NDI documentation, their API, because how NDI defines a sender is not exactly the same way that NMOS defines a sender in a strict sense. So in our documentation, we will refer to a native NDI device or a native NDI receiver when we're talking about the behavior within that NDI SDK. And then we simply use the term NDI device, sender, receiver when it is something that is in true NMOS language. This is an NMOS sender receiver, which is an NDI device. Now, a native NDI device may also be an NDI device, but not necessarily. So a native NDI device may also, that does implement the NMOS extensions will then therefore be an NDI device by the description in our documentation. Okay, so let's look at a couple of the use cases. So here we have a fairly standard sort of environment. We've got an NMOS controller. We've got a couple of NDI devices here. And then we have our RDS, our Registration Discovery Server. So we fire up our devices. They're going to register themselves with the RDS. The controller, through the query API, can then learn about the existence of these devices and what resources they have available. If we wanted to make a connection from device A as a sender to device B as a receiver, we would use the ISO5 connection API, and it would then instruct device B to subscribe to the stream that is generated by A, much exactly the same as we would do in a SMPTE 2110 environment. In this case, all devices are NMOS compliant, so we have full control over everything, full visibility over everything. Similarly, over here on our blue, we have devices X and Y, and these are not NMOS-enabled devices. So the way that these work are completely within the NDI domain. So, as we mentioned, we don't want to break anything in NDI. So, device Y will, through NDI's discovery process, discover device X has a stream available, and it will subscribe to it using the NDI SDK. We also would like to be able to have this device Y to subscribe to that NMOS device A, and it's going to use the NDI mechanisms for discovery, much as it did when it was talking to device X. Again, not breaking our rule that we don't want to preclude normal NMOS behavior. So this device A can accept native NDI connections just as it would if it was not an NMOS device. So there's actually a final use case, which is probably the most interesting, which is I would like to have device A receive a stream from device X. Now, in this case, in the NMOS domain, there's no knowledge of device X. So we don't have a mechanism through the RDS or the query API to know that, to tell device A that it can connect to device X. So what we put in the specification is that this is allowed. However, the controller has to discover device X by its own means. So there's a couple of ways that they can do this. It can implement NDI discovery. So it can use the NDI SDK to discover the devices, and then through ISO5, it is going to instruct device A to connect to device X through the information that was discovered through the NDI discovery. Really important thing is that at no time does device X appear in the registry because it is not an NMOS device. However, the controller is allowed to connect to it, and we have certain rules about how that connection is represented within the status with ISO4 and ISO5 that a connection exists. However, it is connected to an unknown device or an undocumented device. It's also possible the NMOS controller, you have a UI where somebody can just type in a stream name or an IP address, and we don't dictate how that discovery is done, but we say that it is allowed. And this becomes really important because certainly in initial stages of this rolling out, the majority of NMOS devices are not going to be NMOS enabled. And one of the key use cases for NMOS with NDI are gateways that are bridging between a 2110 and an NDI environment. So those gateways can be NMOS enabled, yet they're still able to receive streams from these native devices that are not. So I have a PTZ camera that has 3-year-old firmware and is never going to be updated. I can still have access to that and connect to the streams from that camera with my NMOS to 2110 or my NDI to 2110 gateway. So it offers a lot of flexibility right out of the gate without having to have that critical mass of NDI enabled devices before this is useful. Excuse me. Okay, so now I'm going to get into a few of the technical details of how we represent NMOS devices, flows, streams, devices, and so on in the NDI devices in the NMOS. So first of all, our flows. So we use a media type of application NDI, and the format is a MUX. NDI flows are MUX flows. They may contain audio, video, and metadata. So in the NMOS structure, we create the sender is a MUX, and then there are subflows that would represent the individual audio video subflows that are contained within that flow. So the video subflows, depending on whether we're using high bandwidth NDI or HX, are slightly different. High bandwidth, we specify the video as raw, and HX, we will specify whether it's an H.264 or 265 based on the codec. Now, with NDI high bandwidth, the video on the wire is actually compressed. It's using the SpeedHQ codec. However, the interface that enters and leaves the NDI SDK, the video goes in raw, comes out raw. What happens once it enters that SDK is up to the SDK. You can, to a certain extent, control how it's going to encode it on the wire, but through certain settings, it will optimize that. It will play with bit rates and so on. So rather than trying to guess or make our best estimates as to what that encoding really is, we basically specified that the video is raw, and so at the boundary of the NDI domain, that's what's going in. With HX, the device actually the device itself handles the compression H.264, 265. So that's what's interfacing at the boundary to the NDI domain. So that's how we specify the media types. And it's similar with the audio. With NDI high bandwidth, it's uncompressed audio that goes in and out. So we use a standard PCM type, L16 or L24 or L20, whatever. NDI-HX uses AAC, which is represented with the media type MPEG-4 generic or Opus as the currently supported codecs within NDI. Key thing here is that metadata is not specifically modeled in NMOS for NDI. And the reason for that is that metadata implicitly travels with the video flows. So we don't have a mechanism to independently carry a metadata subflow. So there would be no way to make a connection or model that flow. Also, NDI metadata currently does not conform to metadata that we see in 2110 or SDI environments. It's kind of its own thing. So we don't have standardized closed caption or timecode flows that are easily translatable to something that's in another domain. So, and finally, NDI supports bidirectional metadata. So when I make a connection, for example, from a device to a PTZ camera, we can start receiving metadata from that, but it also opens a back channel that allows control of that PTZ camera within the NDI stream connection. So again, this just started adding more and more complexity that we've just chosen that we're not going to model that. We are, again, going back to basics and saying what we want to do is we want to facilitate a way for devices to be discovered and connected. So modeling of this metadata was not really necessary to achieving that goal. So receiver capabilities, basically fairly straightforward, that we need to have in our receiver capabilities need to support this new media type of application, NDI. NDI groups are handled with a new extension to group tags, the existing group tags. So we can add whatever groups the NDI flow is included in will be added into these tags. Looking over at ISO 5, there's a new transport type, which is this NMOS transport NDI. And importantly, there's no manifest file. So NDI, unlike RTP, does not use SDP to describe its flows. Instead, we have defined a new set of transport parameters that define how the flow is created and how the connection will be made. So it looks something like this. And we have some of these parameters are mandatory and some are optional. So our mandatory parameters that a sender must publish and a controller must push to a receiver in order to make one are the machine name and the source name. And this maps to the NDI domain that looks like this, which is machine name with source name in brackets, one-to-one. So this is the minimum information that's required to give to NDI in order to make a connection. The rest of these parameters are optional, and these can be used to make connections easier with an NDI. So stepping back on how NDI connections are made, NDI runs its own internal discovery mechanism. By default, that's done through MDNS, which has network scope limitations. So when I pass it a machine name and a source name, the receiver actually uses that discovery mechanism to try and figure out what the IP address, port, protocol, and so on that's going on for that sender, and makes the connection. If, for example, that device is in a different subnet and beyond the scope of my MDNS, it's not going to, the connection will fail. And this has been one of the limitations, certainly in earlier versions of NDI, that couldn't escape the current subnet. So in that situation, we do allow the controller to specify a specific IP address, source port, and a URL. So these are all parameters that can be passed to the NDI SDK to aid in making connections. The of important note, the URL is actually considered a proprietary information in NDI. So the NDI SDK specifically says you should not try and interpret this, which basically indicates that the format of this is going to evolve over time and through versions of the SDK, and they've chosen not to expose what those might be. However, within the NMOS environment, it's still useful because a sender can publish it, and then we can take that information and patch it directly to a receiver, and it's NDI's information to do with it what it will to make the connection more robust and more repeatable. The last parameter that we've got on here is the interface IP, and this is for the receiver only. This allows the controller to bind the connection to a specific port on the receiver. So this is basically what we've put into BCP 007 to facilitate discovery and connection within the environment. But what if I need more control? What if I want to be able to adjust quality, or I want to be able to change the codec, or I want to change, dictate that the device is using multicast versus unicast? We've basically determined that those are device-specific or implementation-specific settings. As I said, for example, codec settings, transport, metadata, and so on. So these are out of scope of what we've defined. They could be exposed by a device and controlled through IS-12 or through Katina. But they are not core to the activity that we're doing with BCP 007, which is really focused on discovery and connection of NDI devices. So where are we at with this activity right now? It's still an activity in process. So we have a draft specification complete. The final draft of that is about to be published on GitHub. I'm just waiting for somebody to sign off on it. And we're in the process of developing test plans, which we hope to have done by the end of May or so. There still have some to-dos. We need to implement test cases. This will be added to the AMWA test suite, so we can have that for validation of controllers and nodes. And we also need to do some POC testing with some example implementations to prove out that everything we specified truly works and there's no ambiguity and so on. So that's where we're at. That's what is happening with NDI and NMOS currently. If you're looking for information, it's published on the AMWA website, the URL there, or that QR code. The docs are on GitHub at this address here. And, if you have more questions, feel free to contact me. If you're interested in getting involved and would like to be an early adopter, I'm really happy to speak with you, because the more early adopters that we can get on board, then this will be easier to prove out and elevate to a full standard and get wider industry adoption. So you can reach me here. This is my contact information, and I thank you very much for coming today. Are there any questions?